So this is just a recap of nuclear physics so far. Not necessarily every detail that we've talked about, but we learned about three main types of decay. These pages that you're going to be looking at will be part of a unit review handout you'll get next week. There's alpha decay, and alpha rays are composed of alpha particles. Beta rays are composed of high-speed electrons. There's nothing wrong with calling the particles in beta radiation beta particles, but they are electrons. And gamma rays are composed of gamma ray photons. Here's a diagram showing the stream of those three main types of decays passing through a perpendicular magnetic field. This magnetic field happens to be in. We didn't talk about this before, but I had mentioned, this was a different diagram in your notes, I had mentioned how much more severe the deflection of beta particles were. And the reason for that is, even though they only have half the charge of the alpha particles, which means the alpha particles experience twice the magnetic force, they're so tiny. Electrons have very little mass. So if I apply a certain force to a little tiny Austin Mini car on the highway, it changes direction very rapidly. But if I apply that same force to a Peterbilt truck, big semi-truck, it's not going to move as much in terms of the directional change. This is a graphic that I showed you before. I don't think we really talked about it in detail because I was in the middle of a demonstration at the time. But I do want you to notice something, that when you look very carefully at the alpha particles, they're those red dots. They're pretty big because they're alpha particles, 2 protons and 2 neutrons. When you look at the beta particles, they're tiny, tiny blue dots on this diagram. Those are the electrons in beta radiation. And then in this graphic, I don't know where I got it from. It looks like it's scanned out of a textbook. The gamma radiation is drawn as a wave. And paper is enough to stop the alpha radiation, aluminum is enough to stop the beta radiation, and lead is enough to stop the gamma radiation. You know, you need a thickness of each of those. It's not a single sheet of paper necessarily, or a single layer of aluminum, but you get the idea. In terms of biological damage, when you stop radiation, the reason why biological damage takes place is because the cells that do the stopping absorb the energy that the radiation had. I mean, if a car is suddenly stopped by hitting a concrete barrier in a test run for seat belts or airbags, and it hits a concrete barrier, that energy goes somewhere. Now, in the case of a car, it goes into the car, but it also goes into the concrete barrier. In the case of an alpha particle, it's not like the alpha particle when it's stopped by cells. It's not like the alpha particle is going to get dented like a car. It can't get dented. All of the energy is absorbed by the cells. Since alpha radiation is easily stopped, that means when this radiation hits you, you're absorbing the energy of the alpha radiation more than the energy of the other radiation. I mean, if gamma ray photons go right through you, yeah, they're going to damage a few cells along the way, but they're moving at the speed of light, and they're going to clip a few cells along the way. The analogy I used before is valid. When an alpha particle is stopped by a layer of skin, it isn't stopped by a collision with one cell. It's like a bus being stopped by a whole bunch of cars in a movie, in an action movie. That alpha particle hits a cell and loses a bit of energy, hits another cell and loses a bit of energy. And we believe, or I'm told anyway, that it can be upwards of 10,000 different cells that get damaged in just stopping a single alpha particle. And it stops in the thickness of your skin. So that's 10,000 cells potentially in a very concentrated area. If you get lots of cells like that, and cells multiply, right? And if the cell's damaged, it's going to reproduce itself as a damaged replica, then you're going to get eventually cancerous tumors. By the way, if you ever ingest anything that's radioactive, that's where I don't want to suggest being around it is always safe, but ingesting it is worse. Because then you carry it with you for your lifetime, which is shortened because of that. You should be very comfortable today, by now, writing out the products of alpha decay. So if I told you radium-222 undergoes alpha decay, you should be able to predict the value of the top number of the daughter nucleus and the bottom number. Just a quick reminder that the top number is nucleons and the bottom number is charge. I mean, sometimes the bottom number is protons, but not always. So the bottom number is always charge. And then you can look up 86 on the periodic table. Gamma decay. If I told you lead-207 undergoes gamma decay, then you get lead-207. There's a difference between those two lead-207 nuclei, though. The nucleus on the right-hand side is more stable, and it has less mass. And we indicate that the nucleus that was excited, that had more energy to begin with, is the one on the left by putting an asterisk there. Beta decay, I guess you just need to memorize that during beta decay you get a 0, -1 beta particle or electron, and it's always accompanied by an antineutrino. And then you can add up the top numbers and see that you get 14, bottom numbers is 7. You look it up, that's nitrogen. Positron, oh, and by the way, you ought to be able to figure out what the net change is. And I know when we did this in class, I wrote down, 6 protons, 14 neutrons, etc. I think most of us can just look at this now and see that we go from 6 protons to 7 protons, so we lost a neutron and gained a proton. Positron decay, well, you need to remember that it's a positive electron accompanied by a neutrino, and you ought to be able to figure out the product by looking at conservation of nucleons, conservation of charge, and you ought to be able to figure out the net change. Are you with me on that? Okay. Electron capture is the final thing that we've learned about. I'm bypassing, I don't want to review mass defect and binding energy. During electron capture, an inner electron of the atom is captured into the nucleus where it joins forces with a proton that's already there to turn into a neutron. And in the process, a neutrino is emitted. So I'm putting this because it's almost always on a diploma exam. If they describe electron capture, they throw in this last little nugget of information, that the nucleus you get is almost always unstable, and through a series of gamma ray emissions, it settles down to a stabler state. Note that when you do this, it's the electron that's written on the left-hand side now. And not that it makes a big deal of a difference, but I would prefer to use E here and beta elsewhere, because beta or beta negative decay and positron decay are called beta particles, whereas this is called electron capture. I don't think it really matters though. You ought to be able to figure out, using conservation laws, the charge on the bottom and the number of nucleons, and figure out what it is.